All right. So we've been talking about energy, and we're going to move from just talking about energy momentum into actually talking about work and how energy in the system could change over time. So we'll go ahead and get started with that. I did just update my laptop and iPad, so hopefully this looks good on your end, and hopefully there's no bugs. So we'll go ahead and get started. So let's think about some of these initial questions. So let's see, we've talked about conservation of energy, where maybe we have gravitational potential energy, something falls and that turns into kinetic energy, that whole conservation idea. So under what conditions is energy conserved? So clearly there's sometimes it is, sometimes it isn't. So what are those conditions where this actually works out to things being conserved, and when are they not? How does the system actually gain or lose energy? So if there's a book sitting on the floor, well, there's no gravitational potential energy. There's no kinetic energy because the book's not moving. So how does that energy get in there if we were to like lift it up and put it on the table? Where did that energy come from that suddenly gives it the gravitational potential energy of being on a table? So the question is, are we a part of that system? Are we external to the system? Are we in the environment? That kind of idea is what we're going to talk about. Of course, we're going to talk about how energy is transferred into and out of a system, just like my previous example with picking up a book. That would be us putting energy into the system. Then again, are we part of the system? Are we part of the environment? We'll discuss that. And then, of course, just the definition of work. Okay, so the whole idea of work here is essentially, you might think about it as like, oh, I'm doing something, I'm being productive, I'm working. And that's kind of how you can think about the physics definition of work. It is very much a, there's a process going on, and it is quote unquote doing work, and we can actually calculate the output, the amount of work done by this process. And that's what we're going to be thinking about when we get into the definition of work here. Okay, energy is transferred into and out of a system by pushes and pulls. Okay, so we can have energy going in, and we can also have energy going out. All right, now pushes and pulls, these are all like mechanical interactions. Come on, there we go. Okay, so these are all like mechanical interactions where there's physical touching of the system. Maybe a box being pushed or pulled across the floor. So that's the idea of how we're actually mechanically transferring energy into and out of a system. So these pushes and pulls, that's what's doing the work. Okay, so these applied forces. A system can be characterized by two quantities. So if whatever system we have, we can talk about its kinetic energy, okay, and we can talk about its potential energy, which you all should be familiar with. So again, the kinetic energy is the energy of motion. Okay, this is important. So an object can have an energy just from moving, anything with mass, as long as it's moving. You will have some sort of kinetic energy associated with it. Turns out photons or light particles, they actually also have energy, but that's, even though they're massless, that's a different topic. That's just by the way. If you're curious, you can Google it. But beyond having kinetic energy, and that being the energy of motion, these systems can also have a potential energy. And this is, again, the energy of a position. So where something is can actually dictate how much potential energy it has. Potential energy is also dealing with interactions between objects. So you could think of maybe like a spring and a ball, and then the spring having a potential energy, being able to, or at least having the potential to move the ball. That'd be an interaction between two objects. Now the sum of the kinetic and potential energies is the mechanical energy. And I believe in a previous lecture we've talked about this. But just remember, in general, the whole idea is that you can actually add up the total energy of the system, kinetic plus potential, and that's just your total mechanical energy. Now later we're going to talk about other types of energy like the thermal energy in the system. But for now, we're just going to keep mechanical energy related to the kinetic and the potential. Now, if we move on to thermal energy, like I just talked about, we can't really throw this into the mechanical part. Okay, the mechanical part has to do with like touching and forces or objects interacting through touch. Thermal energy is essentially energy from heat. Okay, and that transfer of energy through heating something up, or if something is cooling down, it's losing thermal energy. So the whole idea here for thermal energy is essentially you've got the microscopic motion of atoms. Remember the balls and the springs? That's a wonderful way to think about these molecules and molecular bonds, because that's a way that we know we can store energy. We've done lots of examples of springs and balls and storing energy that way, and molecularly it's very similar. So the whole idea is essentially you can take these molecules and atoms, the total energy of the bonds, okay, so the bonds between the atoms, that's essentially where that thermal energy is stored. So if you put in some energy and things really get moving, well, that's an increase in thermal energy. If things are starting to slow down and the energy dissipates, well, that's an example of losing thermal energy. Okay, so that's really coming from the bonds between atoms. Oops, I have an extra between. I'll get rid of that, okay? And that is the system's thermal energy. Of course, I've alluded to this, but the thermal energy is associated with the system's temperature. Okay, so more thermal energy, higher temperature, and a higher temperature does indicate that there's more microscopic motion. So those bonds are just really going for it. Now, mechanical energy is transformed into thermal energy through friction. So we do have this whole idea of mechanical energy. So remember, this is kinetic and potential energy. Okay, that's mechanical stuff from touching and things moving, physical objects moving. Okay, this does get transformed into thermal energy because there is in fact that friction. There's that touching, right? So that's the mechanical part. Mechanical energy is transformed into thermal energy through friction. So we're going from physical touching of two objects. That's going to cause them to actually start heating up. Like if you were to, I don't know, take the sleeve of your shirt, start rubbing it, you can actually feel that friction increasing the temperature of both your hand and the shirt. So that's the whole idea of EMEC going to E-thermal. So the system energy is actually, we could define it, tap something onto it here as essentially, okay, so here's our system. We can define it as the mechanical energy, EMEC, plus, okay, so remember this is our kinetic and potential energy. So we can have the mechanical energy plus, let me see if I can grab, yeah, here we go. We can have the kinetic energy plus the thermal energy. Okay, so now putting those two things together, two different types of energy, we actually get the system's total energy, or the total energy of the system itself. So continuing with the idea of thermal energy here. Yeah, okay, so kinetic and potential energy can be transformed into thermal energy. Thermal energy is not normally, okay, changed into kinetic or potential energy. So this is a pretty big deal. You can imagine if we could actually take the thermal energy like from brakes, you could actually power your car with just the energy, the heat energy released from brake pads on a car. Yeah, if you could do that, you would be rich and famous. But it turns out that's really, really hard, if not impossible, to actually reharness that energy. So what we're looking at here is this idea that kinetic and potential energy, it sort of only goes one way, right? So we have, oops. So we have these two types of energy, kinetic and potential, but it's only a one-way transformation to thermal. Okay, I've included that over here in this image as well. We'll get to that in just a second. So energy exchanges within the system. Okay, so the thermal energy could still be a part of the system. Remember, we described it as part of E system. Okay, so these changes are still within the system. Changes of energy within these systems is actually called a transformation. Okay, so it's going to be really important that you keep in mind that this inside the system is a transformation, because we're actually going to start talking about transfers of energy and transformations of energy. Okay, so we got two different words that are similar going on, but they mean very different things. So in this case, we have energy transformations. These energy transformations, because they're within the system, they do not change the energy of the system. So you can see our system, we've got it defined over here. We have our total mechanical energy, right, which is our kinetic energy plus our potential energy. And we can go back and forth, just like if a roller coaster or something is going down, having kinetic energy going down a hill, losing potential energy, goes up again, gains potential energy again, loses kinetic energy. We can transfer back and forth as many times as we want to. However, the rail and the wheel, as the roller coaster car keeps going through the track, we're losing some of that energy to friction. So if we define our system to be like the track and the car, the total energy in that system is conserved, it's not changing, it's just we're losing some inside the system, the sum of the kinetic and potential energy to heating up the track. We can account for it, right? We can still add everything up, which you can see here. We can still add all of that up, and the total amount of energy is still there. It's just we're losing some of it to a process where we can't get it back. So, of course, a system, just like the roller coaster and the track, or whatever system you'd like to define, a system is always situated within an environment. Okay. So we do have environmental influences that we have to think about that act on the system. Okay, so unless the system is completely isolated, it has the possibility of exchanging energy with the environment. Okay, now a lot of times examples I like to use are like satellites in space. Those are pretty much isolated, and energy exchanges there. If you're thinking about maybe a satellite needs to rotate, all of that momentum is conserved, or if a satellite needs to do some sort of maneuver, a lot of times that energy is conserved inside of it because there's not really a lot going on in space. So there's not a lot of environmental impacts that could actually affect what this satellite's doing. But otherwise on Earth, where every system we have is going to be nested inside of some environment, this is where we have to worry about it. So an energy exchange between the system and the environment is called an energy transfer. Okay, so here's where we've got a new word. We have an energy transfer where we previously talked about transformations. Okay, so now we're moving to a transfer. And this is essentially just when the system actually interacts with this environment. Okay, so the mechanical transfer of energy to or from the system is called work. Okay, so to or from the system, so this is going to be in or out of the system. Okay, so we have if work is positive, it indicates that work is done on the system. Okay. So this is important, on the system. So in my first example, if we were to reach in, take a book, put it or pick it up from the floor and put it on a table, we did work. Okay, work is done on that book, floor, table, earth system. We reached into the system, we added some potential energy, so work was done on the system, that therefore the work is positive. Now, if some system has some energy in it, and it loses that energy to the environment, well, then that's going to cause a negative work. Okay, and that's work done by the system. So essentially, we don't have to do anything. We're getting that work out of the system itself. We just have to sit there and let it happen. So that's where we get the negative work from. So we can look at our picture here of our system and environment. Remember, everything inside this box is in the system. So if we transfer energy from like kinetic to potential or kinetic to thermal energy, all that we can sum up, we know that it's conserved. But if we have all these transformations going on inside, and at the same time we have energy being pushed in or pulled out, that's where we have changes in that internal energy. Okay, so again, energy going in means a positive value for work. That means we're adding extra energy, maybe adding kinetic energy. And then if for some reason that energy leaves the system to the environment, well, that system's doing negative work, okay? Because that's losing energy and the environment's somehow absorbing it. So do remember that these interactions with the environment are energy transfers, and energy inside the system where it's just moving from one form to another, like kinetic to potential, that's an energy transformation. Okay, so here's our basic energy model. This is basically the diagram we just looked at. I can go back to it. So this diagram in equation form is what we're looking at, okay? So if we have a change in the system energy, remember, any changes in the system energy, they're zero if the system's isolated and all of those energy sources are just transferring from one to the other. Internal changes in the system means that there's no change in the overall total energy. But there is a change in the overall total energy if we have a change in the overall mechanical energy or we have a change in the thermal energy. Okay, well, we can actually break this up a little bit more. Okay, well, we can say that, well, if we have this system and its kinetic energy increases or decreases, and its potential energy increases or decreases, and this is not from just internally changing from kinetic to potential or potential to kinetic. This is, we have K plus U, but then that total, the total is somehow changed. So maybe we're adding kinetic and potential or something like that. So if we're adding to that total energy, that's where we actually get a delta E system here, okay? So if we get some sort of input, mechanical input or a thermal input, okay, so we change by temperature, anytime when we change the total energy of the system, regardless of what's going on inside, that's work, okay? So energy transferred into or out of the system, this is what we're looking at. That change in the system's energy is just equal to W. Now, again, energy transformed within the system, we're still here at the change in the system energy 0. So now we should ask the question, well, how much energy does a force transfer? Okay, because that is how a system and then an object outside the system, that's how they're going to interact. They're going to interact with some sort of force, right? So the natural question is, well, how can we calculate how much work one of these forces is doing? Okay. So how might an applied force actually do work on some particle? Well, we know that an applied force causes an acceleration just from Newton's second law, We've talked about that a lot. Anytime you apply a force on a particle, it's going to speed up. If you apply a force on an already moving particle, it might slow down. Okay. Now remember that Newton's second law is just F equals ma, and that means that there is a change in velocity, right? Because the acceleration is dv dt, and by definition, acceleration does mean a change in velocity. Okay. So anytime a force is applied, we have a change in velocity. Okay. Well, if a particle or an object is actually moving along some sort of trajectory, as you can see here in this figure, right? So my particle is moving from S initial to S final. So moving this way, okay? Now it's moving along a straight line, but you can see that the force acting on it, see our total force here is not pointing along that line. It's actually pointing off up somewhere else. So maybe this is, you know, a kid pulling a wagon up a hill or something, because the angle of the, just draw it, the angle of the handle on the wagon, you know, it could be at some angle theta. So even though that there's a part of the force pulling upward, there's still a force actually pulling the wagon up the hill. So the whole idea here is, well, the part of the force that's actually doing work, or the part of the force that matters, the part of that force is actually just the part that's parallel to the path that this object is taking, right? So we only care, if we look back at my little diagram here, we only care about that part of the force, right? So if we had some force, it'd be F cosine theta, because we want that adjacent piece. That's really the only part of this force vector that's actually moving the cart along the s-axis. We don't, it's clearly not coming up off the s-axis, so we don't care about the vertical component. Okay, so it's important to realize that the parallel component here is what's actually changing the particle's speed, okay, as it accelerates up the hill. Maybe this force that's pointing upward is, maybe it's not a hill at all. Maybe this upward part of the force is actually what's causing this thing to rise, sort of go into a higher position of SF instead of SI. I don't know. So who knows? Maybe it's responsible for that piece. Doesn't matter. Only thing we care about is the path this thing's actually taking up. The green arrow I've drawn, and the part of the force that's pushing it in that direction, or at least moving it, is this little parallel component. So the idea is that there is a component of a force doing work on a particle. And what happens is that force doing work on a particle essentially causes a change in velocity, right? And remember, that's what's going to add or at least change our kinetic energy in our system. Okay, so this force is doing work because it's changing the kinetic energy. Remember that the kinetic energy is 1/2 mv squared. So we're actually changing v. Okay, so that's why our kinetic energy is changing. There's a change in velocity. We know that from Newton's second law here. Okay, so let's think about Newton's second law and actually get into going from Newton's second law into a force calculation. All right, so we have F equals ma, which again just equals m times dv dt. Now we're going to do something clever. We're going to take the chain rule and we're going to rewrite dv dt. So I'm just going to take this piece here and I'm going to do some clever calculus. Now this trick only works if you have nice, well-defined functions. Maybe you've learned about this in like Calc 3 or differential equations, but you can do this with just any function. Fortunately for us, the functions we use are all constrained by nature, therefore they're usually well behaved. So what I'm going to do is I'm essentially just going to add a ds to the numerator and a ds to the denominator. You can see them here. Those cancel out. If you think about these just as little tiny differentials, the ds in the numerator and denominator They cancel, and I'm still left with what I started with. Because remember, I have dV/dt. I don't want to change that, right? Because then it's not an equation anymore because it's not equal to what I started with. So I still have my dV/dt. It's just I've included these somewhat arbitrary ds values in the numerator and the denominator. But that's okay because what you'll notice is now I have this ds dt. Well, that's a change in distance. We're just using s instead of x or y because it can be any axis. So we have a ds dt. Well, that's distance over time, or change in distance over change in time. Well, that's just the velocity. And then we have this awkward little dv ds. Just coming along for the ride. That's okay. The main point here is that this is still just a dv dt in our original equation. Okay, so we can actually just take this and put it back. Okay, I've done that here. So the cool thing is we can actually just multiply this ds over. Now I have a f ds, and then I still have my mv dv, okay, on each side. Well, this is starting to look like an integral, so why don't we just integrate on the left side? We'll integrate across a change in velocity, so an initial to a final velocity. And then on the right-hand side, well, now the right-hand side is actually an integration across a distance. So we'll go from some initial distance to some final distance. Okay, so here you'll notice I'm actually integrating a force over the distance that it's acting on, whereas on the left-hand side, I'm actually integrating a momentum across the change in velocity that's happening. Okay, so you'll recognize this essentially as a momentum. All right, now let's talk just a little bit more about what's going on here. So when I do this integration, you'll see that this side just turns into a kinetic energy. So we have a final kinetic energy, and we have an initial kinetic energy. Okay, now this still equals an integral of f ds. I don't know what f sub s looks like. I don't have a specific function for it, so we're just going to leave it general. And it turns out what's going on here is essentially, well, that's just delta k, a final kinetic energy minus an initial kinetic energy. Okay, well, we know that delta k from previously, delta k equals work. So therefore, we can just make this other jump and say, well, work must be the integral of the force or a force acting over a distance. So whatever force it is, integrated over however long distance-wise it acted, that's the work done by that force. Now you'll notice that work is force times distance, so the units are joules, and this is just the same as energy, okay? So that is important. Units are important. All right. So this leads us to the work-kinetic energy theorem, which we've kind of talked about, where work done by a force equals a change in kinetic energy. We're going to add to it because we analyze this with just one force, but what if there's like 5 forces acting on something? Okay, so let's think about it that way. When we have several forces acting on a particle over a distance, we have to sum up the work done by all those forces. Okay, so when one or more forces acts on a particle as it is displaced from an initial position to a final position, so as we take some particle, so maybe this is SI, and we move it to some final position, SF, okay? When we do that, with all those forces are acting on it, we could have maybe 10 forces pushing on this thing, who knows? So maybe we have, I don't know, there's 2 forces acting on this particle. So the net work done on the particle by these forces, okay, so we have a net work done which causes the particle's kinetic energy to change, okay, and it's changed by the net work done by those forces. Okay, that's the whole idea of the work-kinetic energy theorem, is that you can add up the work done by individual forces, and that gives you the overall net change in kinetic energy. So a system gains or loses kinetic energy when work transfers energy between the environment and the system. Okay. So that's pretty much in words what we're looking at here. Work's done, so this object's going to speed up or slow down. And that's because something in the environment, maybe a hand comes in to push an object, or a hand comes in to slow it down, or maybe the object is rubbing up against something that's not in the system. Maybe there's some part of the environment. So we have that friction, which is going to slow it down. Either way, work's going to be done that way. Now, you might notice that the work-kinetic energy theorem actually looks like the impulse momentum theorem. And it's essentially the same thing. There's just one difference here. So with the impulse momentum theorem, we have a force acting over some amount of time. Okay, and you'll remember that this is essentially the integral of some force or an impulse. All right, so you'll remember that here. Okay, but this is with respect to time, and all we're doing is just integrating over time to calculate the impulse, whereas with the work-kinetic energy theorem, we're integrating the force, we're integrating over the distance that the force acts, and that's going to tell us the amount of change in the kinetic energy or the work done. Okay, so we have an impulse, which is the force acting over a time, and we have the work-kinetic energy theorem. We have work done during an impulse with the force acting over a specific distance. So a force acting over a time interval and a distance. Okay, we've got two things going on. Okay, so that changes the momentum, right? Because remember, momentum depends on velocity. So there's a change in velocity, therefore there's a change in momentum. So you have a change in momentum and a kinetic energy, and the kinetic energy of a particle. Okay, so this is important here. An impulse is created and work is done by a force acting on a particle. So here we have two of these things we've talked about going on at the same time. It's just one of them happens in time space. The other one happens actually in like space. All right, so now we know what work is. How can we calculate it? So we have forces represented as vectors acting on objects. Okay, well, let's see if we can actually figure out how this integral is going to work. So consider a force F acting on a particle with constant strength and constant direction. Okay, so we'll start with actually panel B down here. So we have a force acting on an object. Switch this to red so it'll be consistent with the image. So we have this force acting on the object, which is down here in green, and it's constant in strength and direction. So that means as it moves and gets up here, same magnitude, same direction. Okay, well, the particle moves through a displacement delta r. Okay, so I'll do a dotted line. So our particle moves some distance. You can actually see it in the top panel here. Some displacement, which is delta r. Okay, so the force vector, F, okay, well, we know it makes an angle with respect to the displacement vector, okay? Our displacement vector, of course, is going to be a straight line. So the component of the force vector along the direction of motion is going to be F cosine theta. Remember, when we talk about work, we only care about the part of the force vector that's actually causing the movement. Okay, so here is the part of the force vector that's actually causing this thing to move across delta r. Okay, so we actually only care about the parallel piece. We can get that parallel piece just by taking cosine theta, just using trig to get that adjacent component. So this is the component, okay, this isn't the force, but this is the component of the force that is responsible for changing the particle's velocity, okay? So this is all done by F cosine theta, not completely F, but that one component. All right, well, we know now, we can plug this in. So we know what our F sub S is, right? This is what we were after. We weren't sure what it was. Well, now we know it's just the force, whatever the force is, and then cosine theta because we want the adjacent piece. We want that piece that's actually pointing in the same direction as the motion. So F sub S is now F cosine theta. Well, F cosine theta, if it's, constant and the force isn't moving around like crazy, we can pull that out front, right? That's just a constant, so it can go in front of the integral. Now we're just left with integrating across ds. Very easy integral, right? So that's just the final position minus the initial position because this limit or this integral has limits. So it turns out the S final minus S initial, that's just our delta R, or our change in displacement, okay? So according to the basic energy model, work can either be positive or negative to indicate energy transfer into or out of the system, right? So remember, this is into, out of the system. But now here's something to think about. F and delta R are always positive, the way we've got this set up. Okay, so that means the sign has to be determined by the angle. Okay, so if F is always positive and R is always positive, right there, the angle theta is actually what's going to determine whether we have work done on the system or work done by the system. Okay, now we can actually simplify this a little bit. If you've had Calc 3, you may be familiar with dot products. We'll talk about exactly how this works later, but what's actually going on here is work is essentially just the dot product between the force vector and the displacement. You'll remember that the dot product is actually just that calculation of a projection, right? Whatever vector you have, when you take the dot product, you're actually just projecting it onto an axis. So we can actually be really clever since we want that projection of F and just use the dot product. But that's still just F delta R cosine theta. So if you want to calculate it that way, maybe you don't like calculating dot products, totally fine. So let's think about this some more. We have this whole idea of the angle is actually deciding if work is being done on the system or by the system. So here we have a couple different scenarios. Let's look at these and talk about them. So in this first one, we have some ball, some object. Okay, and it's got a force acting on it. I'm going to see if I can zoom in a little bit. Okay, so we have this force acting on it. Notice that the length of the force vector, I'm going to change to make it consistent. The length of the force vector, it never changes length, so it's a constant force. The direction never changes, right? So I've got my theta here. The direction's always 0, or at least it's always fully, the angle's always 0, so it's always fully perpendicular with delta R. And you'll notice that since the force is being applied from position 1 to position 2, right? Anytime we apply a force, we have an acceleration. So you'll notice that the velocity vector does get longer, as expected. Okay, so it turns out that in this case, the work done is actually F times the displacement, right? Cosine of, there should be like, a cosine of 0 here. But cosine of 0 is just 1. So we get the full amount of work possible done right here. The sign's positive because it points in the direction of the motion. So energy is transferred into the system. Okay, the particle speeds up. Now, what we can do is we can actually, okay, let's say if the force isn't if the force isn't parallel and maybe it's offset a little bit. So now we have this angle of theta, right? But there's still a component. There's still a component of the force acting here. So really, we're just interested in this piece each time. This is what we want to know. Okay, that's the important part. So we're going to actually use that cosine theta value here. You'll notice, because there's less force in the direction of motion, our velocity vectors, you can see that it's still increasing toward the final position, but not as much, right? We have less force acting on that particle in the direction of motion, so we don't get as big of a change in velocity as we did in the first example. But again, overall, the force vector is still pointing in the direction of motion, so it's still going to be positive, and energy is going to be transferred into the system. Now, here's an interesting example. So here we actually have the force vector at a right angle to the direction of motion. And you'll notice there's no component of the force changing the length of these velocity vectors, okay? So it turns out delta V is 0, there's no change. Well, if there's no change in V, that means there's no change in kinetic energy. Speed and kinetic energy here are 0. Now, why is that? Remember, that's because the angle theta dictates whether work's going in or coming out. So that angle right now is 90 degrees. Okay, well, cosine of 90 degrees is 0, and we don't even have to worry about a sign, right? 0 is either positive or negative. So that angle, perpendicular, no work's being done. Now I've actually included, I've included an example here. So if you consider a car being held in a curve by friction, right? So you remember, as this car goes around the curve, the only thing keeping it from flying out of the curve is friction. Well, it turns out that a friction force is exactly perpendicular to the path, which means friction does no work, okay? So the force is everywhere perpendicular to the car's displacement. So it does no work. So that is something important. Those perpendicular forces that are holding an object in a circular motion pattern, they're actually not doing any work because they are perpendicular to the path. We can actually keep moving this angle even further and actually make it an obtuse angle. So now we have force where the component is actually kind of pointing away now, right? Because we want that same piece here, that same x component, but it's actually pointing in the opposite direction. So now what's going to happen, or what's going to happen is we have some initial velocity, but because the force is actually generally in the direction opposite to motion, our velocity, our final velocity, is going to be a little bit smaller. Because that angle, remember, that's what's deciding what's going on here. That angle is greater than 90 degrees, which is actually going to cause our F delta R cosine theta to be negative. So what's happening here is energy is transferred out of the system, right? That kinetic energy is getting smaller because the kinetic energy we started with over here is larger than the kinetic energy we end with, okay, in the final position, because that force is actually taking it out. Then we can actually go to an extreme example where the force is directly opposed to the motion. And we could start with a nice v initial here with a nice long vector, a fast initial velocity. But because the force is directly opposed, we get down to a really tiny vector at the end. This v final is quite small. And this is a complete, literally 180. So it's the amount of total possible amount of work you could get, F delta R, but it's negative, right? Because we have that cosine of 180. That's just -1, okay? So the magnitude F delta R is the same as in the original problem. It's just pointing in the completely opposite direction. And that means here, in both of these cases, since we have negative work, energy is transferred out of the system. Okay, so we can sort of break this down like it is here in 3 different pieces. If in general the force vector is pointed in the direction of motion, you have kinetic energy increasing, so velocity increases, positive work, You could have a perpendicular force where no work is done and the velocity stays the same and the kinetic energy stays the same, or you could have a situation where the force vector points in the opposite direction of motion, and that's where you get the kinetic energy decreasing and the velocity decreasing. Right, and the last thing we won't worry about too much since this is just physics 1. If you all go on to take like a dynamics course or classical mechanics, this gets more important. But essentially, work done by a variable force, that's just integrating whatever function may be there, right? So we could have a constant force over some distance, like right here in this first example. Well, that's just the force times the distance, FD. That's a very simple integral, easily done. We could have something like a restoring force, like Hooke's law, where we have, the spring constant times the amount of displacement. Well, if that's our force and we want to integrate, so we want to integrate from like where the spring started to where it ended, well, we can do that. That's actually the integral done here. Okay, so that's just going to be integral of kx, and it turns out the work done is just 1/2 kx squared. Or we could have some crazy function. Even in this example here, we don't know it in example 3, but if we did, it's just a simple integral. Okay, I just wanted to show and remind you that the work done, it really is just an integral or the area under a curve. So that's all for the definition of work. I just wanted to include this last thing, and then all of the examples I'm going to wait until the 3rd lecture, and then I'll finish up a few things, and then we'll talk about several examples of work, like Work-Kinetic Energy Theorem and everything. So just hang with me, keep watching, keep taking notes, and then we'll do a bunch of examples all at once and sort of hit everything. So until then, I appreciate your attention, and if you have any questions, as always, please let me know.